Hey, hope you're all having a good day. My name is Hector, going over question 42. So, seatbelts and airbags save lives by reducing the forces exerted on the driver and passengers in an automobile collision. Cars are designed with a crumple zone in the front of the car. In the event of an impact, the passenger compartment decelerates over a distance of about 1 meter. As the front of the car crumples, an occupant restrained by seatbelts and airbags decelerates with the car. By contrast, an unrestrained occupant keeps moving forward with no loss of speed, Newton's first law, until hitting the dashboard or windshield. These are unyielding surfaces, and the unfortunate occupant then decelerates over a distance of only about 5 millimeters. So there are two parts to this question. There's part A and part B. So we're going to go through part A first. I'm going to go ahead and read that out. A 60-kilogram person is in a head-on collision. The car speed at impact is 50 meters a second. Estimate the net force on the person if he or she is wearing a seatbelt and if the airbag deploys. So I went ahead and immediately just highlighted some things I thought were important in the question. So obviously how far they're going to accelerate over, how much they weigh, how fast they're going, and really what the question is. We're asked to estimate the net force. So kind of just zooming out here a bit. I have some very meager graphs here. So the one on the left, on the very bottom, that is kind of just like a very rough graph of what's actually going on. So we have some car with initial velocity, right, and its impact. And on the right side, like a little zoomed in, basically. So we want to know what the acceleration is, right? This little bit right here, what the acceleration is after this 1 meter long distance, right? And we know that the velocity initial is 15 and the velocity final is 0. So pulling from the class, we're using a few different concepts from class here. We're using, well, obviously Newton's first, right? So basically if an object is in motion, it wants to stay in motion. If it's at rest, it will stay at rest. And Newton's second law, so that's just F equals ma. We use that in class. And we're going to go ahead and set up Newton's second law for basically what's going on, so we can get this acceleration, or yeah, basically. So kind of just going through this, we know that the summation of the forces will be equal to some net force, right? We know that the net force is some acceleration times some mass. So the next step, right, would be to figure out what that acceleration is. So going through those steps, we pull out this kinematic equation. Now, this is the kinematic equation that does not involve time. We are not given a time. You could solve for a time, but it would be much, much more complicated than just pulling this kinematic equation out. Again, this is one given in class, and it's just the easiest one to work with. So kind of solving this out, we get the acceleration equal to negative 112.5 meters a second. And it's negative because it's going in the opposite direction of motion. It's slowing the speed down. So now from there, we can find the F net. And we went ahead and we just plug in our A and plug in our mass, and boom, 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 negative 6,750 newtons. And that is a lot of newtons to be experiencing, even with a seatbelt, even with a thing. Obviously, the situation is more complicated than that, but that's the same kind of thing. So that is really part A for you. We're going to go ahead and move on to part B. So estimate the net force that ultimately stops the person if he or she is not restrained by a seatbelt or airbag. So in this part, we see that they actually decelerate over about 5 millimeters, which is not enough time. So kind of going over here, right? So it's the exact same process. We're going to set up that exact same, basically this F net equation, and then we're going to do the same kinematic, and we're just going to plug in our initial velocity. We know our final velocity is 0 because we're asked when the car stops, so we know that's 0. Kind of going through it, we get negative 22,500 meters a second squared, and as you can already guess, that's going to equate to a much, much higher force than the other one, I should say. So now we can find the F net. Just kind of doing that, we get that F net is equal to about negative 1.35 times 10 to the 6 newtons, which is a lot of newtons. It is a lot of newtons. In fact, I have this little portion over here just to give you an idea of exactly how many newtons is that. So going around 33.6 miles an hour, that is the same thing as 24 times the max bite force of a Tyrannosaurus Rex. So if you decelerate over that short amount of time, the amount of force you feel is absolutely ridiculous. And I mean, this is the same kind of situation as if you were to jump off something high and just kind of take the impact, straight leg it. That would be a very, very bad idea. Your joints would be decelerating over a very, very short distance, where if you were to instead bend your knees and, say, roll, you would be taking that time period and stretching that deceleration out. So it would be less of an impact, less force on you. And that's the same kind of view as happens in a car accident, basically, is you want that longer distance of force, longer distance for deceleration, such that your force is much less. One last thing I found interesting about this was I was really curious, what does it take? What can a human body take as far as newtons are concerned? And so what I seemed to find online was that about 3,000 newtons, somewhere around there, has about a 25% chance of breaking your ribs. So you can imagine the absolute chance you'd have to just be smashed to bits by this absolute force of not having the seatbelt on and hitting the dashboard. And yeah, I think that really just does it for the problem. Again, really remembering Newton's second law is very important in this problem. Just realizing that, that's how you set up the equations. And then having that kinematic on hand so you can get an idea of what's kind of going on there. All right. Hope you all have a good day.